People are programmed to love plants. It plays an important part in the perception of our environments. Their green color is the center of our visible spectrum and signals balance. As a primitive response, when we see plants, we are assured of the presence of water and food. It is therefore not surprising we like to surround ourselves with plants. We are familiar with most of their shapes as we grow up seeing plants. But there is one crucial aspect of plants that we don't really see: pollen. Every year plants release millions of tiny pollen grains. So tiny, about 300 fit on a 1 mm pinhead, that we're not aware of all the pollen constantly floating around us in the air. It is not until the 17th century, with the development of the microscope, that English physiologist Nehemiah Grew discovered that pollen have a lot of different shapes which are related to their species. What he didn't know yet is that this formed the basis of an important branch of geological and geographical science: palynology.
Particularly for the first time, you're often astounded at this beautiful array of different shapes and sizes and ornamentation that the pollen grains have.
Considering a single pine tree can produce up to 1 to 2 kilograms of pollen per season, it is not surprising that the majority of pollen don't pollinate but fall to the ground. Preserved in lake and river sediments, these can be recovered and used to reconstruct past landscapes.
One of the incredible things about palynology, I always think, is that from a tiny sample such as this, we can reconstruct a whole environment.
Pollen studies are also an important driver in the treatment of hay fever and can be used in forensic studies. Imagine this is pollen from around the lake, and this is sand. Both enter the lake sediments and settle on top of older river and lake sediments. This process continues over thousands and millions of years, and the layers are there to tell us about them. Before the beginning of the ice ages, large parts of the northern hemisphere, including Europe, were covered with the famous Sino-American flora. In its main composition, this flora is still present nowadays in Japan, China and North America. During the sequence of ice ages called the Pleistocene, ice forced this flora to move southwards. Unlike in North America and Asia, the east-west oriented mountain ridges and the Mediterranean on the European continent presented barriers to the southward migrating flora, causing a decline in Sino-American flora with each ice age. As every ice age caused a decline in this plant community, Europe has been a very good place for palynologists to identify successive glacial cycles.
That is because there's a range of tree species in particular that almost form a succession of recolonisation after major glacial periods, and so you can trace this same succession or recolonisation through each of the interglacial cycles, and that's very distinctive.
A complicating factor, however, is that at no one place is there a complete Pleistocene succession. It required a fair dose of acumen to collect the necessary pieces of information. So why do we do this? The implication of this type of research is global. We keep crossing planetary boundaries defined by Earth system scientists as the safe operating space of humanity. 3 of those are climate, the nitrogen nutrient cycle, and biodiversity.
There are many scientists that are concerned that basically we are making irreversible changes to the biosphere, and that we're approaching kind of a critical point where the decisions we make in the next few decades could have a huge impact on where we end up in terms of the outcomes.
Primary productivity is the total rate at which the ecosystem captures and stores carbon as plant biomass. About half of this apple is carbon, and it is produced by plants. Studies of palm reproduction using satellites since the 1980s show that currently humans use 40% of this production, with only 10% harvestable production left available to us. This might not even be the only obstacle to our future sustenance.
Researchers from the biological, environmental, geographical, ecological and chemical sciences have come together to explore our planetary boundaries. Their verdict, the use for fresh water in irrigation as well as disturbance of nitrogen and phosphorus nutrient cycles have already been reached. We need to cut by on less water and fertilizer.
It's worth having scientists thinking about the big picture about those things and to sort of make a balanced estimate of what's the range of things that could happen. And even part of the point of the tipping point article is what are the areas where there could be a non-linear response where a series of small decisions could add up to a big effect that we didn't realize.
To plan for the future, we need to account for future climate change. To understand how our biosphere will react, we can look into the past. You just have to look for the invisible pollen. This was exactly what Leonard von Post did when he counted pollen types through layers in peat cores from around Sweden. In 1916, he published the first pollen diagrams. Pollen diagrams show the change in abundance of plant types through location's natural history. At the Australian National University, palynologists are unearthing a vegetational history of nearby Lake George. Since its discovery, the lake has often surprised people as lake levels fluctuate and even drop to naught. It is a perfect rain gauge for the area and so a good regional climate record.
The lake floor preserves a long sedimentary history. It has the longest sedimentary record of any lake in Australia. We now know it goes back 4 million years, and long lake records like that are unusual in the world.
The original record was a much more peripheral record and so had a lot more periods of drying out and desiccation. And it has lots of gaps in it, whereas this current core has the sedimentation appears to be a lot more continuous and has fewer missing periods of time.
We think that with the new core and with some more cores that we plan to drill, that we will have an unparalleled record.
Pollen, while invisible, gives a wealth of useful information, from landscape reconstruction to climate records, to ecological insight on the timescale of ice ages. And they're all floating in the air like tiny pieces of story.